Is it okay? Is it okay?
Yes, sir. Yes.
Yeah. So basically, if you look at the ocean, it is a vast source. Basically the scientific challenge is to study the physical, chemical, biological, and geological phenomena that occur in the ocean and its frontiers with the atmosphere and the Earth interior. So there is a lot of potential in studying the oceanic surface. So underwater vehicles are used for the ocean exploration. This is a great scientific challenge, and we need to know about this scientific exploration by deploying the marine vehicles, or what we call as underwater vehicles. So sometimes what happens that single underwater vehicle or marine vehicle may not be adequate to employ because of vast tasks to accomplish. Therefore, a lot of marine vehicles or marine robotic vehicles are deployed in cooperative motion for the navigation and control for exploring the ocean floor. And however, there are certain technical challenges. Like the challenges are that what are the methods and instruments or control we need to have the marine data acquisition, and because of this scientific this is of interest to scientific and commercial as well as civilian applications. So we need to know a lot of about the data fusion, signal processing, and then the dissemination of that captured information for several regions. Now, what we usually do, that kind of exploration can be done through divers. So, or to the latter extent, it was also seen that marine vehicles are employed for this oceanic exploration. But there are poor maneuverability and the poor 3D and time coverage, and also the cost of employing a marine vehicle is quite big. So therefore, the recent trend is to use the remotely operated vehicles, but still we need to make them autonomous by cutting the umbilical call. So what we do is that we go for the autonomous underwater vehicles to accomplish this task. So what benefit you get by that? We get high maneuverability and autonomy, very least amount of interference or of the the sorry very least amount of interference about the human intervention is necessary. So therefore, it is very much appreciable to go for the autonomous underwater vehicle for the oceanic application. So, but what is the the challenge here? The challenge is to have an efficient guidance and control. Basically, we want to have a motion plan to achieve the desired orientation. So, where the objective is to force the orientation error to zero, that is the actual orientation should be tracking to the desired orientation. So basically this guidance and control of the underwater vehicle, we need the computing and control to be designed carefully with the different sensors, and so therefore we need quite a lot about how to design good controller, how to take care of the uncertainties, how to take care of the external disturbances, and we how to employ good sensors and data acquisition systems and navigation systems to accomplish good guidance and control of this underwater vehicle. Now, what you do is for this guidance of one of the control for the underwater vehicle is called path following. So there is a desired path, and then we need to follow this desired path. So while doing so, we need to have the heading also to control the heading directions. So So basically, if you look at the AUV, means on autonomous underwater vehicle structure, so it has basically either the stern or the thruster, which basically gives the actuating force to them. As a matter of fact, we can control their orientation and heading as you require for particular task. So look at the AUV, kinematics and dynamics. We have basically source detection and roll, pitch, sway, yaw, and heave. So these are the different degrees of freedom. So accordingly, we define the different variables in different degrees of freedom, and primarily we choose the earth fixed frame or the body fixed frame to define the kinematics and the dynamics. So if you look at this AUV for the steering motion, if you go over the top view, you'll see that this is the nose portion and this is the hull portion and this is the tail, and this is the stern, and we put the rudder somewhere here. So the we define two different variables. One set of variable UVR, those are defined in the body fixed frame, and the XY psi, these are the variables which are defined in the universal frame, and where u is basically the surge velocity, and v the sway velocity, and r is the yaw rate, whereas x and y are the inertial coordinates of the sorry, underwater vehicle, and psi k the yaw orientation. So now I have given a brief introduction what is an AUV or autonomous underwater vehicle. Now its control is a challenge. Why it is a challenge? Because compared to a usual mobile robot, the autonomous underwater vehicle control has serious control issues. For example, the underwater vehicle has to interact with a oceanic medium where there are a lot of uncertainties in the external environment. For example, the oceanic current, it is very much uncertain to model it, and therefore this uncertainty comes in the dynamics of the underwater vehicle, as well as the like the hydrodynamic effects, which is very difficult to accurately obtain. And also the model of the underwater vehicle is quite nonlinear because of all these same correlations and like centrifugal forces, and then their interactions and so many things. So in view of that, many of the people who they work on the underwater vehicle control, they linearize the model and then design the control for that. But true sense, that neglect of this nonlinearity in the dynamics does not provide us the accurate whatever we desire to obtain the correct orientation or the heading control performance we may not get accurately. So therefore, there are a lot of research challenges for this underwater vehicle modeling as well as control. This is truly a nonlinear, robotic system, which is basically, and the additional difficulty what you take care of here is that in the oceanic medium, the communication is a little difficult than what it happens in the surface medium. So the data rate is very low. So the data rate is low, then the uncertainty because of the ocean current, because of the hydrodynamic effects, because of the interaction between the several degrees of freedom, and because of the different sensors, their fusion, and then the other difficult aspect is the under actuation. The under actuation means the number of control inputs to a system, if it is less than the number of degrees of freedom to control, so it is an under actuated system. So controlling an under actuated system is a really difficult task. So in view of this, we have chosen machine learning, an advanced machine learning technique called extreme learning technique for modeling the underwater vehicle, and then we design so many controllers for the dynamic controller and the kinematic controller for the heading control of an underwater vehicle. And this work is the detail of this work can be found from the article that IIT Cyber Systems and Robotics published in 2019. So what basically our objective is? Our objective is to design a nonlinear model predictive controller by using the model that we derive for the underwater vehicle using the machine learning technique called extreme learning technique. And then we verify whether this controller, that is the nonlinear model predictive controller, based on the model we identify, is accurate enough to give us the path following task as we desire. So what basically the heading control of an AUV? So basically we define the acceptance region, and then we have the you have the AUV, and we define the different waypoints. These are the different waypoints. So where the xi minus 1 0, yi minus 0, these are the previous waypoints. And then the next waypoint is xi0 or xyi0. So these waypoints are basically connected by rectilinear path. So then what is the job here is that we want to, in the step 1, we want to find out the acceptance region. So whether it is there or, so then we have to design a line of sight control technique, that means to develop a control law such that the underwater vehicle tracks the desired waypoints using the line of sight guidance algorithm. Once the AUV reaches within the defined acceptance region of a waypoint, then the next waypoint is allotted for tracking. So the tracking problem is converted to a waypoint tracking problem, and then the whole objective is it should be remaining within the acceptance region. Then what we do is we define the kinematics for the heading motion, and then we discretize the continuous time kinematics equation to the discrete domain by employing some Euler finite difference approximation method, in which we choose the sampling time t and k, the sampling instant, and therefore we get the discretized equation for the kinematics of the AUV for particularly the heading motion, where I already defined the psi k, that is the orientation, and rk, and already we defined, and u and r are the the u and v and r are the velocity and the rudder positions, okay, inputs. And similarly the dynamics of the heading motion we define in the continuous time system, and then we employ the discretization approach by the finite difference approximation. We convert this continuous time dynamics of the AUV for the heading motion to the discrete time dynamics, in which our delta r here, the delta r, particularly here delta rk minus 1. So this delta r is the input to the rudder plane, and this nr and nuv, these terms nr, nuv, and u delta r are the hydrodynamic coefficients. So what then we do, we then translate that equation to corresponding discrete equation. We write those equation in very compact form. That means we write that this is the cosine and s for the sine, and these two like the kinematics and dynamics we summarize here for the heading motion of the AUV. Now what we do is we developed a prototype underwater vehicle in the laboratory, in which what we do is we have our the body, the structure we design, then these are the turns, and then we make a provision for the DVL, the Doppler velocity log, and the GPS, and we put a single board computer and the Atmega data acquisition system, and we put the batteries here, and the depth sensor, we have the inertial navigation system, and we have the DC-DC converter, which is powered by the battery. So that the control and the sensor, computing platform and the sensor we embed here in the system, and the AUV is fabricated in the lab. And what we do is we then our objective then is to identify the dynamics of the AUV by using some sort of machine learning algorithm. Because if you go back to the nonlinear system identification literature, you will see that one of the very famous model structure used is called the Narmax model structure, that is nonlinear autoregressive moving average exogenous model. What you do there, we have the set of inputs, and then we set of outputs by employing the tab delay lines, or the what you call the z to the power -1, and then you train the, or you get the plant output and compare with the estimated output. Then you get an error, and that error you use to tune the whatever neural network or etc. for modeling purpose. But this neural network training and using a multi-layer perceptron sometimes is not a feasible solution, because these neural networks may give there are problems with the local minima and also the convergence problem. So therefore, we are interested to go for a reasonably accurate model by employing the machine learning. And what you do is we then translate these dynamics and kinematics to a representation of what is called as z hat k plus 1 equals to f z k uk, where f is a nonlinear function of any identification is a mapping from the input space to the output space, or input domain to the output domain. So what you do here is that we define a augmented state zk, which comprises of vk rk, and uk the input, that the radar input. And then our purpose is to identify this function, nonlinear function, by employing the machine learning algorithm. So what you do is we have chosen the ELM, the structure, model structure, and we have the hidden layers and their bias and the outputs. This is the AUV plant, AUV the prototype AUV, and these are the states. And what you do is these states, whatever measurement you do in the, we capture the data from the autonomous underwater vehicle prototype system, and then you feed them to this neural network for training purpose with this ELM model structure. So then we get the training. So then what is the training here? So we have the augmented states, which are the function of nonlinear function of the states. And where the input to this network is basically zk and uk. Zk is basically the vk and rk, and our purpose is then we write the so basically by employing this ELM model structure, we have the weights and then the inputs, and this is the bias. And then what is you can translate this equation in form of a like a least square representation. That means phi star and w, where this phi star is the output matrix of the hidden layer and w is the weight matrix. So then our problem boils down to get the optimal set of weights, optimal set of these hidden layer weights, and such that this should be in least square sense it is minimized. So here we have the NH is the number of hidden layer nodes, and W and WH are the output weight and input weight vectors, and this eta is basically the regularization coefficient, and Y0 the desired output vector. So then our problem is now to identify the dynamics of the AUV by considering the input VK and RK, and del as the del RK the output. So our purpose is how accurately you can get the model by or ELM model of the underwater vehicle dynamics. So then one of the aspect is that how to choose the number of hidden nodes. So to fix the number of hidden nodes, we start with a heuristic approach. Then we employ a mean square criterion to fine tune it to get it. So the where y hat k and yk are the predicted output and actual outputs of the network. The nodes where the MAC is minimum during the training and validation process gives us the optimal number of hidden neurons that would be used for the ELM model. So then once you find out how many hidden nodes we will be selecting, then our next job is to optimize the hidden layer parameters. So for that, different evolutionary computing techniques can be employed, and one such technique is called Joya algorithm, and that is used. What it done? The experimental data set is divided into training data set and testing data set, and we then initialize the number of candidate population, design parameters, for example, the hidden layer parameters of the ELM model, and then we start ELM means ELM and E for the evolutionary computation. That is the Joy algorithm, and termination criterion. And during the training phase, each candidate population vector is initialized randomly with a range -1, 1. And for each candidate, we calculate the hidden layer parameter matrix output using this equation. I told you earlier this equation, that is we want to minimize W with this this is the error, because this output of the hidden layer weighted minus output, and this regularization constant, and then this the norm of this one, the square. So once you get the mean square error between the actual and the estimated value, then select the best solution and worst solution by comparing the MAC, the of all the candidates in that population, and then employ the Joy algorithm vector. Once you do that, then you find out the best set of population that gives the global minimum, and that value store it for the optimal hidden layer parameters. So then what you do in the ELM, the training phase, one is the offline training phase, which we do using the experimental data set and train the ELM model to find the output, hidden layer, and output weight vector. Now, once it is offline trained, we go for the online one, because we want to employ this in the online control of the AUV. For that, we set the initial I equal to 0 for each new input output data set, and determine the hidden layer output matrix phi. And then for I equal to 0, you compute two things. One is phi transpose phi, and so these two are basically called the least square solution. For each new input output data, then update the output weight waste on the updating rule. This is very similar to your recursive least square algorithm. So then the new weights and the past weight, and this factor is basically the error, and this is the weight update, the gain updatation approach. So then you iteratively do it till you set some kind of criterion to terminate the training process. So while doing so, we have seen that selecting the potential terms as input output nodes is quite relevant for any model structure. Both input and output lags are given as 4. That means suppose the current input is UK, so we take the past input UK-1, K-2, K-3, and K-4. And similarly for the nonlinear, so the output also we take the lag. Like if the current output is YK, we take the past 4 outputs as their lag in outputs for the training purposes. And then the degree of nonlinear polynomial, if you choose 3, then you see the number of terms in the input vector comes out to be 165. So there is a pruning necessary. The pruning of these number terms will make the identified model complex, and so therefore we want to choose the right kind of input from by using the approach called pruning. So we then, as I mentioned earlier, to get the best set of parameters, we want to use the least square approach in each term of the input vector, and by comparing the error called error reduction ratio, we consider the final input, that is xin. So what to do then? Our next purpose is to design the controller. So this, if you look at the structure, the controller for the AUV that we propose here, we have the waypoints we define here, xt and yd, Then we have a kinematic guidance law that I explained, the waypoint tracking I explained, the region of acceptance. That will give you the RD, the desired value, the desired, that goes to the nonlinear adaptive control design. And then we have to set some actuator constants. And then what you do is we then find out because this is the real prototype AUV, and what you do is for control design we need its model. So we derive the model by employing the machine learning, that is ALM, and this TDL, the tap delay. And then what you do is we basically this control comprises of two components. One is called the kinematic controller that takes the position XY and heading orientation psi of the inertial frame as input and evaluates the desired angular velocity r. So that desired RD is being used as the input to the dynamic controller and generates a rudder control input delta r in face of the input constraints, that is the rudder plane constraints. So here the control objective is, with the given future reference trajectory, the control objective is to formulate a predictive optimal law that will drive the future system output, that is r hat, near to the desired value. So r hat is the future input to the desired value, that is RD. So what you do is the design of, so we design two controllers. One is a kinematic controller, another is the dynamic controller. In the kinematic controller, what you do, we let us look at this, like waypoint tracking. We define different waypoints and then connect them by different, paths. For example, a linear path, and then we calculate the heading error, that is HEK, that is the previous waypoint to the current waypoint, what is the difference in the XY positions, and then we translate that HEK by using the kinematic equation into this form. Then what you do is we apply adaptive control here by using using a concept of backstepping control, which is very popular nonlinear adaptive controller. That means we define a Lyapunov candidate function. What is half? It should be a positive definite function. So Vk is a Lyapunov candidate function, that is half He square, that is the heading. So any square is a positive, so therefore it is a positive definite function. So by using this Lyapunov function at each sampling time, we then design a backstepping controller, and then that backstepping controller will give us the desired yaw rate, that is RD, and that RD is used here in the dynamic controller. So then our next job is to design a dynamic controller using a concept of model predictive control. And the NMPC stands for nonlinear model predictive controller. So here our objective is to determine a predictive optimal control law such that the predicted output will follow the reference trajectory. So what you do here is that we define a cost function J, which is basically summation of two terms here. The first one is the this NP, the prediction horizon, and NU stands for the control horizon. And this EK, so this K plus J means given the error at time K, to predict the error at K plus J, and this is some weight, and then we have our control. That means the control is also weighted here. So our purpose, the purpose of designing this model predictive control is to predict J step ahead, K plus J, with certain constants. The constant is that the in order to avoid the actuator saturation, or then what you do is we must have a constant over the control. That is why, so the range is U min and U max. And then similarly, the incremental control, del U min and del U max, there is also a constant here. And similarly, the output has a constant Y min to Y max. And then what you do is we generate these errors, that is the the reference rudder position and minus the actual whatever you estimated, and then this is the control, the delta u, you compute the current control minus the previous control, that is -1. So by this we formulate a cost function, and need to be optimized. So what we do is we use this concept, the model predictive control concept, to design the dynamic controller. So by choosing appropriately the design, the backstepping approach and nonlinear model predictive approach, we get the composite control of this underwater vehicle for achieving the heading control of the system. So in which also we take into account the different constraints, that means to avoid the actuator saturation and also to go for the desired heading angle control. So what we do is we implemented these algorithms, the kinematic and the dynamic control, what you developed, and so three aspects we consider here. Number one, we employ the ELM approach and the training and its optimization of its hidden layer parameters. The ELM model we obtain for the resulting ELM model we obtain for the AUV, and that AUV model we use for the dynamic controller, and the kinematic controller will give the reference value of the rudder position to the dynamic controller. So once you design all these, then our next job is to implement the same to verify the efficacy of the controller. So we first implemented this controller using MATLAB. And then for initialization, we choose the heuristic approach of initializing the initial weights and the hidden biases randomly at in the range of -1 to +1. And we choose the hyperbolic tangent function as the activation function. And all the AUV states, as I mentioned, that V and U and V and R are initialized to 0. And then what you do is we select the input vector, different input vectors R and U, and what is the corresponding error reduction ratio. So then this big input vector, if you see that if the error reduction ratio is in the range of very less value, and then if the error is less, then we choose the then which corresponding which training phase you get the best set of this ERR, so that you return as the best ELM model that we obtain for the AUV. So then what you get, we choose a desired ER orientation, that means with different timings. So during 0 to 50 it is 0, and 50 to 100 it is 1.57, and 100 to 150 it is 0, and again 150 to 200 is -1.7. So what you do is we compare the controller performance for different variable or different performances. One of them is the heading orientation that is obtained with different controllers. So what we do is we have designed a nonlinear model predictive control, in which the model is identified by using the ELM or the machine learning, and the kinematic controller is designed by using the backstepping approach, and the dynamic controller is designed by the model predictive control. And two of the recent controllers, one of them is a H infinity state feedback controller, and the other one is an inverse optimal self-tuning control. And where we compared all of them, and we found while you compare the tracking performance for the heading orientation, we find that the proposed one, the red one you see here, it gives the better tracking of the desired heading orientation compared to the rest two. So similarly, if you look at the control input that is needed for the actuator, in case of the proposed one, you see there is no much oscillation or sudden change in case of the proposed controller as compared to the two other recently reported. One is the H infinity, the second one is the inverse optimal. Now you see the heading angle error. While it is tracking, you see the proposed one has less error compared to the rest two. And similarly, if you compare the heading orientation, we see that the I think it is the proposed one gives the better accuracy. Now, if you compare in presence of the noise, you'll see that the with noise also, if you see with noise, you can find even there is the control input little oscillatory, but the heading orientation is closely following this desired orientation. Now we have also seen the performance of this nonlinear model predictive based dynamic controller. We have taken one step ahead, predicted ELM model using tracking of desired spine kind of trajectory in the XY plane. So this is the XY plane, and this is the kind of tracking we are expecting. That means you see this is the blue one is the desired one, but we define the waypoints and connect the waypoints by the rectilinear paths to go for a line of sight control. And what you do here is that we see the velocity and the control input you compare. We'll see that the control input is is very much restrictive, not requiring more control, and as the minimum the appropriate control is generated, and we find out the desired and the actual rates. You find that is accurately tracking. Now what we do is we also compare the non-linear model predictive controller performance for the waypoint tracking. So we define different waypoints like 62. These are the XY coordinates. 160. So these are the different waypoints. So the starting point and the destination, and then we find out what is the corresponding radar position. And then next we compare the estimation of the dynamic model using ELM structure. So how do you say that the ELM model, whatever we obtain, is basically the good model? So for that we compare the MSE, the mean square error, and based on the minimum mean square, the error, the optimum value of the number of hidden layer is chosen. And then these basically gives this blue and this red. These are the two different MSE curves corresponding to training and validation. And then what you do is we can also optimize this number of hidden nodes by using the Joya algorithm and the PSO, the particle swarm optimization. We'll see that in case of the Joya algorithm, the training is better than the PSO. And then what you do is we estimate the dynamic model of the AOV using this. We have other parameters to see that how best the model is behaving. So we compare the predicted output and the experimental. So from the experiment set, we have taken the output, and then we have the the blue one is the actual output we obtained from the experiment, and the red one is the predicted. And you see that the estimation of the error rate is quite good. And now therefore, since estimation is good, the corresponding prediction error is very much less. And we find the autocorrelation coefficient of the prediction error, and we see that what is the confidence interval to authenticate the number of lags, and then what is the autocorrelation coefficient for this prediction error. Then we also experimentally validate the performance of the proposed controller during tracking of a heading orientation. You see here the red one is basically the actual heading of the rate, and the black one is the desired. So then you see the actual one is rightly tracking the desired one, and corresponding tracking error is shown here, and tracking error comes to 0. Now we have also seen that the experimental result that is obtained for tracking during heading orientation. So we see here this is the actual, the black one is the actual, and this is the linearized rate, the red one, and we see the corresponding control input. And the control input, you see, we have defined an upper bound and we also defined the lower bound. So this upper bound, so then the control, the meaning of the the control signal whatever is generated, that remains within the upper bound and lower bound. So therefore we can ensure that the actuator saturation is prevented. Now, what basically we conclude from these results, that we design a new control scheme for an AUV, autonomous underwater vehicle, by identifying its dynamics using ELM model structure by using the machine learning ELM algorithm. And this advanced machine learning technique increases the model accuracy corresponding compared to the simple neural network model by employing either a multi-layer perceptron or maybe RBF, whatever. And the number of hidden layers the hidden layer parameters are optimized by using a very popular evolutionary computing approach called Joy algorithm. And the backstepping approach is employed to design the kinematic controller. In the backstepping design, we choose the heading error, and therefore we translate the heading error in terms of the kinematic equation, and therefrom we find out the desired R or the rudder position or velocity that would be given to the dynamic controller. So then what you do based on the kinematic controller, we obtain the desired velocity. Then that desired velocity is used in the design of a model predictive dynamic controller. That dynamic controller is basically designed using the approach of predictive control, and it's optimal in the sense we define a some step ahead output and the error, and then we have some cost function. In that cost function, we give the weightage. We give the weightage to both the output as well as to the control input with certain constraints, and based on that constraints, and we optimize the cost function, and then that cost function, once you optimize, you get the control law, and that is basically used to achieve the desired orientation. And we also consider the disturbances and noises while tracking the trajectory, and we have seen even if there is some disturbance in the system is there, but the controller is good enough to handle it and then track the desired orientation. And we have first simulated all these algorithms in MATLAB, and having confirmed that it is doing well, we then proceed with a prototype development, prototype AUV real-time implementation. We use the robot operating system to interface all these sensors, and we use a single board computer where you dump all these exe files of the control there, and you then implement this real-time control algorithm. And then we verified this heading control algorithm not only in real time but also in the swimming pool, and we have seen that the desired orientation is rightly tracked, and the proposed controller predicts the heading dynamics of the underwater vehicle accurately and keeps the control input within the actuator saturation limits. So as I have shown you the figure where the control has the upper bound and the lower bound, because one of the major problem of this controller is the actuator saturation. So in order to avoid that, what we do, we have defined the control constant in the cost function. So we ensure that the control signal remain within the upper bound and lower bound, and as a matter of fact, the actuator saturation is avoided. So a couple of references, like one of these reference is the nonlinear system identification, and then we have the machine learning. This is a good paper on machine learning, and then we have the predictive control and the model predictive control. And some of the publication that arose from this work is basically, one is this extremum learning based nonlinear model predictive control for an autonomous underwater vehicle. So the IT cyber system and robotics. and the other one is online external learning algorithm based identification and non-remote predictive controller for waypoint tracking application of an underwater vehicle, that is IT, cognitive computation and systems. And one is that cognitive, that is modeling, cognitive information computer modeling. So this is another reference we have used for this one. And I must thank my students who have work hard to develop the prototype AUV and simulating the control algorithm and implementing the real-time algorithm in the prototype AUV and verifying this efficacy in the swimming pool. So with this, I have finished my part. So any question, I will be happy to answer if I can.
Yes, sir. So there are many questions. So I'll
Yeah.
take one by one.
Yeah.
The first question: does the hazy environment underwater affect the direction of path?
Yes, because as you see the oceanic, the waves, the ocean current. So these are quite uncertain. Uncertain. We cannot have any measurement to have that. So it is a quite disturbing factor.
Okay. Then next question is, how are the hindrances caused by large sea animals and coral reefs tackled?
Say again, please.
How are the hindrances caused by large sea animals and coral reefs tackled?
So this question actually I cannot answer perfectly, but I can say a little bit because this is little different than my area. But the scientific exploration for the oceanic, the animals, the aquatic animals, is a big task, and really poses a big challenge for the big animals or maybe aquatic animals than the smaller ones.
And the next question, sir, in case of uh, if the connection fails, how the
Mhm.
vehicle navigate the direction underwater?
Yeah, that is a very good question. Actually, what happens? This is the drawback of like the communication, whatever efficient communication, acoustic communication you design, always there is a problem in the data communication. Now you might be knowing that the data is being sent in form of packets. So that we call in the language called packet dropouts. So when there is a packet dropout, what usually is being done, we estimate the two things. We estimate the two things. One is the communication delay and the packet dropouts. And then what you do is we use an estimator. We use an estimator to estimate the kind of delay, and then by virtue of that estimation we know that how the information can be so suppose one instant the information is sensor information is not available, so by that time we have our observer, we design a carefully an observer or estimator that will give you the right information to continue with your control. It will not jeopardize the motion control of the AOV.
Okay, sir. Then one more question. Can reinforcement learning be used with deep neural network to improve the performance of AUP?
Yeah, that's a very good question. Actually, we have already done that. We have already used reinforcement learning, in which basically what happens, we use an actor and a critic. So what happens is that this actor means the control at current instant. It generates the control action looking at the dynamics or uncertainty, whatever you call, or the disturbances. Then it sends to the critic. Critic then gives if it is good, if it is improved one corresponding the past sampling time, it then adds a reward factor. So in this way, we move on completely in a positive direction of improving the performance. So reinforcement learning is also a machine learning algorithm. It is certainly very much useful for controlling the underwater vehicle motion control. So it's really good. Good.
Sir, there is no more question. current interest. Very nice. So there is no more question. Sir, how is the Joy algorithm
Yeah,
efficient than
yeah.
PSO?
So we find in this particular application, this joy algorithm it gives us the improved or the optimal values. But a lot of things have to be again analyzed why it is giving improved values theoretically. We have not done that. And there are a lot of evolutionary computing techniques. So we can there is no particular algorithm we have converged, but as of now only we tried these two, the PSO and Jaya. So interested readers or maybe those who are working in the area can try the recent ones possible.
Okay, sir. And you applied extreme learning algorithm.
Yeah.
So, why did you, I mean, chose this algorithm? What was the
Yeah.
properties it has?
Yeah, basically, if you
Extreme.
look at this, the number one is that compared to the if you compare the simple neural network, let us say single layer neural network or a multi-layer neural network, and using a back propagation, there is
Right.
always the local minima and all that. Number two,
Yes.
we want to have a real-time control, so we cannot train so much because it is in the loop. So therefore we want to have a very fast kind of model and accurate model. And another advantage is that as I mentioned, this AUV is truly a nonlinear system and there are a lot of uncertainties are there. So to model it accurately, we if you go exactly with these many work that have been reported like neural network or maybe Narmax modeling, it may not give you a very compact model because as you mark here, by virtue of the ELM and this optimization by algorithm, we have obtained a very reasonably accurate model of the AUV. That's the reason why you go for the ELM.
Thank you, sir. So, is there any consideration for depth of water?
Yeah. Depth of water is the heading control only, that heading direction. Because we have taken heading is not a difficult task because heading is the straight vertical direction. But the orientation, heading, with the orientation that is and velocity, three things are together. We have taken three things in conjunction.
Right, sir. So I think there is no more questions, and your presentation was really superb and uh, very. I mean, the application underwater application is really. I mean, it is a kind of application which will make uh, the researchers to think about different type of, I mean, this type of dynamic applications. Generally computer science students, they did not go for this kind of problem, and I think if they collaborate with electrical electronics people, they could have um, start this kind of research work, and for future help if they need at any point of time, I hope they you will not hesitate to extend your cooperation. So they might contact you, they might take your help, and this is the only objective and motive of arranging this 6-day lecture series. So thank you, sir, for your marvelous presentation. And on behalf of everyone of our university, I would like to extend a very warm thanks to you for accepting our invitation and giving this presentation. Thank you. Thank you so much, sir.
Thank you, madam. And really, it was a privilege for me to talk to people who are interested in machine learning applications, and particularly this underwater vehicle robotics. This is a very much interesting area, and it is also a interdisciplinary area where the computer scientists have a lot of things to contribute in terms of the sensor design, in terms of the machine learning, in terms of the computation. So many things are involved here. So I am happy if anyone is interested to collaborate, and we have a lot of collaboration in this. I have collaboration with Naval Science Technological Laboratories with DRDO, and we have collaboration with France, collaborations with UK and Russia. So many projects are running. So if anybody is interested, please, my email ID is there on the first slide, the title slide. Please do let me know. And wish you all the best. And thank you once again, madam, for inviting me.
Thank you, sir. Thank you.
Thank you. Thank you.
So, thank you all participants, all viewers of this session. And again, let me inform you, we have another session which will start exactly at 11 a.m. And the speaker for that session is Professor Lance Chun Che Fang, and he will speak on a subject, I mean, which might be, you might feel it very interesting, IEEE resources and initiatives in AI and machine learning. So he is a very reputed academician and has a very vast year of experience. Definitely, he will provide you a lot of information, and you people will get lot of not only information, but again you may find some. There is a possibility you can explore to collaborate with him. Okay, thank you all. Again, we will log in just before 10 minutes before 11 a.m. So thank you until then. Thank you.